Hi, I'm Duncan Cameron. I'm the Professor of Plant and Soil Biology here at the University of Sheffield. I think I learned to kind of embrace and enjoy the kind of shock and surprise when people meet me for the first time, thinking they kind of know me professionally. I was recently giving a keynote at a conference in Oman, and I was being introduced by the British ambassador to Oman, and he kind of went through my career, and I was getting very embarrassed, and then I stood up and there was this kind of audible intake of breath as they made the connection between me and this person that was being described, and I rather like that, because I think it puts people slightly on their back foot, and it gives you a little bit of an advantage when it comes to kind of meeting people for the first time and kind of building relationships with them. I think I call it the fluffy bunny syndrome, and I think it goes back to the deep root in education. You're kind of taught about plants as these passive things that just sit there and photosynthesize, and that's about the most interesting thing about them. And animals seem so much more interesting. They're more animate, and they're cute and fluffy often. But some of our most enigmatic organisms are plants. I started my career working on plants that are parasites of other plants, and also working on the orchids, and those are two incredibly enigmatic groups of plants. And I think when you start to learn about their biology and their life history, you realise they're every bit as exciting as animals. In the 19th century, a very famous German biologist called Anton de Bary described symbiosis as the living together of unlike organisms. Now, I think that's a useful definition, but I don't think it goes far enough. So if I were to take Anton de Bary's definition, I would say the intimate living together of unlike organisms, and I think that intimacy is really important. But a lot of people, myself included at the start of my career, kind of thought about symbiosis as two organisms working together to their mutual benefit. Now that's a type of symbiosis, and that we call a mutualism. But if you think about my definition, a parasite is also a symbiosis. So we have this whole spectrum of different symbioses. Some we want, some we don't want. And actually we might be able to use one symbiosis to control another symbiosis. So symbiosis is absolutely embedded in life, and it helps us produce food, but it's also one of the biggest challenges to agriculture. 80% of all plants that currently live or have ever lived have an intimate symbiosis with a fungus, and the only way they can survive and take up the nutrients that they need from the soil is by giving energy from photosynthesis. So the plants make sugar, they give that sugar to the plant, it uses that energy source, and the fungus goes out into the soil, and it can access the tiny little pores in soils that plant roots are just too big for. And of course, fungi have completely different chemistry to that of a plant, so they can chemically take up and release nutrients in a way plants can't. So I developed this 4-step model, which has basically been the foundation of a lot of my research since, in terms of understanding that relationship at the immunological level. So effectively, when you're a beneficial fungus, you come into your host plant root, and your host plant has to defend itself because it doesn't know at that point if you're friend or foe. So the plant recognises characteristics of the fungus. We call those MAMPs, and these are the kind of patterns on the surface of microbe cell walls, the molecules that they're made of that stick to them, that allow the plant to recognise that another organism is inside it. And when it does that, all hell breaks loose. The plant's alarms start ringing, and it starts to defend itself. Now, what I'm really interested in is the process that then follows when those two organisms start to talk to each other, and they send each other signals, effectively, hey, what the hell are you doing here? Don't worry, I'm your friend. And those signals can then cause that local defence to turn off. which is great, so the symbiosis can develop. But like us, when we get infected locally by something, we can have a whole system response. So when plants recognize a pathogen, one of the first things they do is send signals throughout their body to say, hey, I might be being attacked, get ready. And the legacy of that then means that even this mutualist, this beneficial fungus colonizing the plant root, the legacy of that interaction can leave the plant in the primed state. So as soon as it's in this primed state, it's better able to defend itself against pathogens. When these symbioses start to form, they don't just change the signals that they send to each other, they change the signals that the plant sends out into the environment as a whole. So the way a plant recruits a beneficial microbe is by, again, talking to it using chemistry, and it sends signals out into the soil to say, hey, come and find me, which will cause bacteria to swim towards the roots and to reproduce within the rooting zone to help the mycorrhizal fungus break down the nutrients. But of course, those are bacteria. They might be harmful too. So the plant goes through this same process of preparing its immune system for attack. So you often see this, what we call synergistic effect, where the priming of the plant defences is simply more than the sum of its parts. The plant is more ready to defend itself than it would if either one of those two organisms had found its way into the roots. From my research, we know that the use of pesticides and herbicides actually damages those really important microbes that you find in the soil. We've effectively sterilised our soils through ploughing them, through pesticides, and actually through putting too many nutrients into those soils. So I think we need to move away from this very high input model of agriculture to a low input model. But when I say a low input model, I don't mean a low tech model. I think what we can start to do is, using our much more advanced understanding of how plants and microbes in the agricultural environment work, rather than resorting to the chemical option as the only option, we might think there's a biological option too.